Hi there. Thank you so much for coming to my talk today. My name is Aaron Skinner. I'm a PhD student at the University of British Columbia in Vancouver, and I'm in Claire Kremen's Works lab. Before I get started, I want to recognize that UBC is on the traditional, ancestral, and unceded lands of the Musqueam people. And today I'm going to be talking about size gradients in nightjars. But before I dive into that, I want to start with some indigenous folklore about this species that you're seeing on your screen right now, the eastern whippoorwill. Um, the eastern whippoorwill is a species that's very dear to, and near to my heart. I worked with the eastern whippoorwill during my master's. But in many indigenous groups' folklore, the whippoorwill is a very bad omen. If the whippoorwill perches outside of your window and sings, that is thought to signify that you or one of your loved ones is going to die. So here's the sound to be aware of. So I don't know. I personally love whippoorwills. I had so many whippoorwills always singing outside of my window when I was doing field work with them, and no untimely deaths for me or anyone close to me. But do what you will with that information. So Bergman's rule. Bergman's rule is that warm-blooded animals will be larger in colder regions than in warmer regions. And this particular writing of this rule says that it's within a taxa, but this has been applied both within and between species. And so the underlying sort of theory behind that motivated this rule was the surface area to volume ratio. You can see here in these four cubes that the side of each cube increases by 2 centimeters. Um, so the same increase in each consecutively larger cube. Surface area and volume both increase, but the surface area to volume ratio decreases as the cubes get larger. And this is important for thermoregulation because metabolic heat production scales with volume and the capacity to dissipate heat scales with surface area. So a bigger organism with a smaller surface area to volume ratio, in theory, will produce more heat and uh, won't 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 struggle as much to maintain that heat due to the relatively smaller surface area that they have. So there has been general adherence to Bergmann's rule, both inter-specifically and intra-specifically. But I think nightjars are a really interesting group to examine Bergmann's rule in because I think there's a reasonable chance that they won't follow this pattern in body size. And the reason that I think that is because they have all these other evolved ways that they can handle extreme environmental conditions. So to handle the cold, these three species here are able to exhibit at least some amount of torpor. So that's where essentially their metabolic rate slows down. It's almost like a mini hibernation. And so in periods of low food availability or during really cold periods, they're able to enter this almost hibernation-like state. And then these species are also able to handle really high temperatures, extreme heat as well. They have an efficient evaporative heat dissipation ability, and part of that is due to this behavioral mechanism called gular fluttering, where they sort of inflate their throat and air comes in and out, and that air um, is really effective at heat exchange for with the nightjar's body. And another important life history trait for all three of these species here is that they're all migratory, and so they sort of escape the coldest and harshest times of year in the temperate regions where they breed, but then they winter in much more uh, benign tropical areas. And all of these also have high site fidelity, which is important, as you'll see in a moment. So our study objectives here were threefold. We wanted to examine whether body size increased with latitude, essentially whether these three species exhibited Bergmannian inclines, whether they followed Bergmann's rule. Our next objective was to examine the potential mechanisms behind any observed patterns in body size. So, in Bergmann's original formulation of this rule, he invoked the idea of geography and geography's relationship with temperature. So he said that at higher latitudes, species will be, or individuals will be larger because of the surface area to volume ratio inherent with biological scaling. And he implied that this was for thermoregulatory reasons. So, due to the colder temperatures at more northerly latitudes. Since Bergmann's original rule, there have been sort of additional extensions, additional potential mechanisms that could explain the patterns we observe where species, individuals tend to be larger at higher latitudes. So I'll just briefly mention productivity, seasonality, migration distance. These also all could explain the observed patterns that we frequently see in relation to Bergmann's rule. So here we captured these three species on the breeding grounds. This top panel here, this top row of plots shows the locations where we captured individuals on the breeding grounds, and then a much smaller subset, about 190 of these individuals, we put on GPS tags. Sorry, much more than 190. We got data from 190 tags that returned, but these GPS tags give you the location of this individual throughout the full annual cycle to about a ten meter accuracy. Um, and so for those 190 individuals, we had information about where they spent their time on the breeding grounds and also where they spent their time on the wintering grounds. And so importantly, we had these two distinct data sets. We had a much larger data set with almost 3,400 captures, and then a data set with information across the full annual cycle of about 190 individuals. So for each individual that we captured on the breeding grounds, we weighed that individual, measured its wing chord, and then we set out to test these different competing hypotheses using an information theoretic approach. And importantly, we structured our models to represent these distinct hypotheses. So, for example, we the geographic pattern hypothesis, we made all the models that essentially we dredged all the potential models from the global model, And then we did the same thing for temperature regulation, productivity, seasonality, migration distance. And we competed all of these models within the same model set and used AIC to evaluate the amount of support for each model. Um, so on with the full annual cycle data set, we had about twice as many models in each model set because we had models using the breeding grounds information and then models also using the wintering ground information. Whereas for the breeding data set, those 3,400 individuals almost, it was just the breeding set, the breeding information went into the models. So ultimately, we had 12 model sets. We had three species, two different metrics of body size, wing chord, and mass, and then our two data sets, our full annual cycle data set and our breeding data set. And as I just mentioned, these the two different data sets had different numbers of models because we had almost twice as many models in the full annual cycle data sets due to the wintering grounds information. Okay, so to get back to our objectives here, do nightjars follow Bergmann's rule? So, as I mentioned, Bergmann originally formulated his rule with regards to latitude. And so we took this first question pretty literally and just examined the parameter estimates for latitude for these three species. And so you can see here that all three of these species exhibited a positive relationship with body size and latitude, and it doesn't matter which metric we used as a proxy for body size. We have mass here and wing chord here, and the patterns are qualitatively similar. All three species do follow Bergmann's rule. Our next objective was to test the mechanism associated with behind these observed patterns in body size. So we looked at the geographic pattern, hypothesis, temperature regulation, productivity, and seasonality hypotheses using the breeding data set. And importantly, these plots here only show parameter estimates from models that were within 4 delta AIC points of the top model. So there's lots of parameters and models that we looked at that aren't shown here because there was almost no model support for those models. What you can see is that the parameters that are here, almost all of them come from the geographic pattern hypothesis. They're all related to an individual's position on the surface of the Earth. So latitude, longitude, elevation, those were the parameters from the models that were most supported in this data set. And so we found support for the geographic pattern hypothesis. And only in the Eastern whippoorwill and in using body mass as our metric of size did we have support for temperature regulation being the most supported model in that species and size metric. And finally, we wanted to know whether information from the breeding grounds or the wintering grounds was more important in determining the body size of these individuals in these three species. And so the mean estimate of each parameter here, sort of this central point, either has a circle if a model from the breeding grounds was most supported, or a triangle if a model from the wintering grounds was most supported. And it's not just your eyes here. There are no triangles on this plot because all of our top models in the full annual cycle data set um, were from the breeding grounds. So again, just in this much smaller data set, 190 individuals, we found evidence that the breeding grounds was the environmental factors or geographic location on the breeding grounds was more influential in determining body size patterns than information on the wintering grounds. Okay, so these plots here are isoclines that show the predicted body masses for these three species across their breeding range. And this is really just to give you all a little bit of an idea of sort of the range that we're talking about here. Um, and I should note that this is the top model from the geographic pattern hypothesis for each species. So you'll notice that these isoclines sort of have different shapes to them, different orientations, and that's because the top model was different in each species. So for European nightjar, it was just latitude, whippoorwill, it was latitude and longitude, and then common nighthawk also had elevation in that top model. But importantly, you'll notice, for example, looking at Eastern whippoorwill, the variation in size is really quite large. It's at the southern part of its range, the top model predicted that individuals were about 55 grams, and at the most northerly part of their range, about 80 grams. So that's a substantial difference in body mass for these individuals, and similar patterns for the common nighthawk, and a little bit reduced in the eastern whippoorwill. So in summary, to wrap it all up, our three focal nightjars do follow Bergmann's rule, and that's despite the fact that they're migratory and have behavioral and physiological adaptations to help them handle extreme environmental conditions. We found that the breeding range was more important than the wintering grounds in terms of selecting selective pressures on body size. And finally, we found the most support for the geographic pattern hypothesis and minor support for the temperature regulation hypothesis just in one species and using one metric of body size. And ultimately, we think that the geographic pattern hypothesis was the most supported overall because these variables were highly correlated with several of the environmental covariates in the different hypotheses. So we didn't combine any of the environmental covariates from different hypotheses. And so the geographic pattern hypothesis was sort of the combine the most information across all of these different environmental gradients that likely play some role in shaping body size in these three species of nightjars. Um, and the final point I want to make here is that I think these findings are important, in addition for just the evolutionary implications. Also, what's happening in light of climate change. Casey Youngflesh showed that species that tend to respond to temperature over space also respond to temperature through time. And so essentially, we document here that these three species did respond in a pattern consistent with Bergmann's rule through space, but also this suggests that they would likely alter their morphologies through time with warming temperatures associated with climate change. And so it's hard to know exactly what that means for these three species, whether these are adaptive changes, whether that's good for these species, so to speak, or anyways, that's sort of a future line of research that we hope we can pursue here. Um, Yeah, very happy to say that this paper was recently accepted in the Journal of Biogeography, so please check it out if you're interested. And huge thanks to all of my co-authors here, um, and in particular Alicia Korpak and Ellie Knight, who were really instrumental in pulling this paper together. So thank you so much to all my co-authors, and thank you all for tuning in.